So these two coming up in follow-up lectures. In this lecture, I want to talk about the formula for the tangent plane. So to find the normal to the plane, in order to find the equation of the tangent plane, we come back to our parameter world. We look at two unit vectors in direction of u and in direction of v. So if you move along these lines, these vectors, something happens along the surface, right? So you move maybe this way. And if you move along the other direction, maybe you move along this in your surface. So they determine two curves, and then they determine tangents to them. So there will be these two tangents to the surface. Now, if you have two vectors that you know are tangent to your surface, you can find the equation of the plane. Any plane is uniquely described by two vectors that are not parallel to each other. But what are these vectors themselves? So the vectors that I just drew for you was partial derivatives of components of R. So by that, what I mean is, first of all, R at uv is a point in R3, so it has some I component, which we write as x of uv. So it's a function of uv. And then the y component of the image is a function of uv. And the third component, similarly, is a function of uv. So we can write any such function this way. If you move along the u direction by 1 unit, that's the partial derivative, then these x, y, and z's react to that, and that will be denoted by this notation. R subscript u will be partial of x, partial of u, and then partial of y, partial of u, j, and partial of z, partial of u, k. I'm suppressing plugging in the UVs in all of these. If we are interested at one particular point, U naught, V naught, we just plug in the values here. So we assume that we will require this quantity at a particular point. And similarly, if you move in the V direction, the tangent will be x partial V, partial y, partial vj, partial z, partial vk. It's not guaranteed for any function, but for parameterization, it's part of the assumptions. We always assume implicitly, even if not emphasized, that Ru and Rv are non-zero. First of all, none of them is 0, and non-parallel. They are not pointing in the same direction, and we know from the picture it's obvious why this is avoided, because otherwise the two vectors wouldn't identify a unique plane. Now you have a plane and you know two vectors in it, so the normal to the tangent plane will be their cross product, right? You have two vectors in the plane, their cross product will be perpendicular to the plane, and any one vector that is perpendicular to the plane is enough. And this cross product of two vectors is still a vector. So that will be the normal vector to the plane, and we know one point that the plane includes, and that will be the point at the value we are interested in. So R of u naught, v naught, that particular value. And here, of course, into these we are plugging in that fixed point of interest. So that is the first thing we can do with parametric description of surfaces. We can talk about tangent planes. all you need to remember is that this cross product is giving the normal to the tangent plane.